All right, let's get started. So last time we talked about this thing called KD trees. So the idea of KD tree is to develop a structure of the data distribution before we receive any queries, so that based on the sort of an indexed data space, right? Whenever there's a new query, instead of searching over the entire space, we could kind of pre-structure the data space into different partitions and using that to facilitate the search. So the idea actually was, well, I should have gone to the um, previous slide over here. So last time we saw the way that we could construct KD trees. So let's say we have 10 data samples. Then what you do is basically to find, first of all, median. I mean, depending on the implementation, it doesn't have to be median. It can be just a mean or, whatever. But usually median is kind of, the common practice, I'll say. And then, find median and then basically switch between coordinates. So in this case, we have, only two coordinates, two coordinate axes. One is the x-axis and then the other is y-axis. So basically we switch between x-axis and y-axis and then, keep calculating the median and then construct a tree according to that. So in this example, we're going to begin with the x-axis. So in the horizontal direction, what's in the middle is P5, as you can see, and that's going to be our first partition of the space. And then, for each of the subspace divided by that first partition, what we do is to then, switch to the y-axis and then find the median along the y-axis. So if you look at the data samples on the right-hand side vertically, then we have P9, P10, P7, P8, P6. And then among those five, what's in the middle is P7. So that's going to be our next partition line. And then on the left-hand side, we have P4, P2, P1, P3. So it's we have even numbers. So in this case, we just choose the one that's earlier in index. So P1 and P2 both are in the middle, but we just simply choose the one that is first. And in that way, we can split the space into now 4 sections. And then for each of those 4 sections, we repeat the same thing, but this time along the x-axis, right? So in this partition, we have 2 points. So the median is going to be P9. In this partition, we only have 1 point. So, there's no need for computing median. We basically repeat the same thing and then just, choose the one that's earlier. And in that way, we can divide a space into smaller sections, and that's basically the idea of k-means KD tree algorithm. So the process that we just illustrated can be represented in this binary tree. So a binary tree is basically a tree-like structure that has only 2 branches for each of the nodes. So the first node is P5 because the first thing that we did was to partition the space into half and half with respect to P5. So that's the first node. And then on the left-hand side, we partitioned the space into 2 with respect to P2. So that's this node over here. P7 is on the right-hand side. So by just repeating the same process, you're going to, in no matter, how your data distribution look like, you'll be able to construct a tree that looks like this. So that's basically the idea of KD trees. Now, what we're going to do today is to take a look at, first of all, how we could, process queries with KD trees. And from there, we're going to discuss if the KD trees are good for big data problems. Okay, we're going to talk about some of the issues of KD trees, what they're good for, and what are the situations that they don't work very well. So that's kind of the game plan here for today. Now, let's consider a slightly more complicated example. So instead of just 10 points, we have now slightly bigger number of points. Okay. So the gray dots are basically the training data set that we have, and we have constructed a KD tree that's on the right hand side over here. Let's say a user input a query point, and then our goal is to find the closest neighbor to the query point, such that similar to like the KNN algorithms, we basically want to classify the query according to its nearest neighbors, or for whatever application. So that's basically the purpose of the objective of this this problem over here. Now, what we're going to do is basically to follow down this tree, and then on the left is just for visualization. So in computer algorithm, what's really happening is on this the tree of the the tree representation of the KD tree. So the very first thing is to go with compare the query point with the head node, which is P5, and then P5 is over here, and then you can simply compare P5 and query in the first coordinates. Okay, so is it on the left? Is it on the right? And based on that, what we know is that the query point is on the right hand side of the P5, which was the reference line. Now, then, that leads us to this node over here, and again, we're doing the same thing. We just need to compare if the query point is above P7 or below P7. So the only difference, with the previous scenario is that, in case of P5 node, we compare the position horizontally, but with the P7 node, we're going to compare it vertically, so along the Y direction. So obviously, query point is above P7, so that leads us to the node of P9, okay? And then over here, we repeat the same thing, okay? And you can actually, well, this is, again, can be different across the way that KD trees are implemented, but you can define the limit of the depth of KD tree. So let's assume that the depth of KD tree is only 3, so we have only 3 nodes, and then everything else is just, clutter inside of this, these boxes. Now, after this search, we kind of chased down from P5 and then visited P7 and then visited P9. And then finally, we came into this bin over here. So that's a bucket that the query point falls into. Now, in order to compute the nearest neighbor, what you're going to do is, first of all, to compute the distance from the query point to all the points in that bucket. And as a result of that, what you will end up doing is to compare the compute the distances from the query point to all the other points in the bucket. And, doing this on the entire set of points versus doing this only on the points that are within the bucket, obviously the latter is, computationally more efficient because you need to traverse only 3 points as opposed to all the points in the space. So in a very efficient manner, you can find a candidate for the nearest neighbor, which is in this particular example, P9. Okay, and with that, you may wonder that, well, P9 is actually not the nearest point per se, because if you look at the point over here on the other bucket, you can clearly see that there's a point that's closer to the query point than P9, right? So did our algorithm fail? No. So for those kind of situations, what the KD tree search algorithms do is to actually visit the siblings in the tree. So if you visited this, what you do next is to visit the sibling. And you visit the sibling and then do the search again on the sibling. Okay. So after searching through the points in this bucket, what you're going to do next is to visit the sibling of that bucket and then do the search again. And then as a result of that search, you kind of converge to a point that is actually closer than P9. Okay, and that's going to be our new updated nearest neighbor. Now, then after visiting that area, then we know within this 2 buckets, we know that this particular point over here is the closest neighbor. Now, the strategy that we have undertaken in order to cope with the situation where the closest neighbor is on the neighboring bucket rather than the bucket that actually the query point is in, we visited a sibling of the current bucket. So if you consider this collection of 2 buckets as one big bucket, then its sibling is going to be the one that corresponds to this one, right? And should we visit the sibling of this big bucket? And if so, then, after searching over this union of these 2 big buckets, then its sibling is going to be this area. So then should we visit the sibling again? And if so, what is the point of doing KD tree if we're going to just visit all the siblings and then the entire space, right? So here's a useful strategy. We visit the sibling only when the current closest distance, okay, is bigger than the distance from the query to the rectangular bounding box. Okay, so obviously the distance from the query to this P7 point over here is greater than the distance from the query to the current closest point. What that means is, okay, even if you do the search over the entire set of points in this bucket, there's no chance for you to come up with a point that is closer than the current closest neighbor, because the boundary of that bucket is far further away than the current closest neighbor. So, there's no chance that there's going to be a closest neighbor to the query point, right? So with that reasoning, we can actually skip the search of this bucket correspond to P6, and then we can just simply gray out the entire P6 node as well as its children. And then we're going to crawl up to the P7 node, and then same thing, we have searched the entire P7 bucket, and then the query point is actually further away from the boundary, the rectangular bounding box, compared to the distance from the current closest neighbor. So again, there's no chance that there's a closest neighbor within this bucket. So without even need to traverse all the points in this bucket, you already know that everything under this P2 node are going to be disqualified. So you don't really need to do the search. And as a result of that, you have just completed the search, and you now know that the closest neighbor to the query point is this one without having to visit all the sections. So if you kind of recap, we visited this section over here first, and then we visited its sibling over here, but then we did not actually visit these sections overall. So if you think about it, the search range is much smaller than the entire data space, and in that manner, you can save a lot of computational time, right? I mean, for here, we have only a handful amount of points, but if you imagine a situation where we have millions of points, then obviously the computational advantage that you will, get from this kind of a tree structured data is going to be tremendous. Okay, so that's basically the idea of KD trees. Now, let us, think about this KD tree in the context of big data. So I'm gonna, jump to this slide. If you think about it, again, when you think about the big data, you have to think about in the context of 3 Vs. Before that, I am seeing a question in the chat that says, can you explain why we don't go to the other buckets again and just its direct sibling? Yeah, there we go. So this is an important part, so it's worthwhile to emphasize that again. So sorry, I just noticed that there was a question coming in the chat bot. So again, let me explain this one more time. So here's a query point, and then the query point gets into the tree, and then tracing down the tree to see which bucket the query point belongs is not a difficult task, right? You just need to do the depth search. Now we know that the query point falls into this bucket, and what we're going to do is to compare this with, well, first of all, we're going to find the nearest neighbor from this bucket to the query point. So that's going to be P9 over here. And what we do next is we measure the distance from the query to the closest neighbor and see if that minimal distance, so that D mean is a current minimal distance, and we compare that with the distance to the sibling bucket, which means P9 is the point that determines the boundary between the left bucket and the right bucket. So by measuring the distance, the horizontal distance from the query point to the P9, we can see if that circle defined by the closest neighbor and the query point touches that boundary or not. So in this case, does the circle touches the boundary, which means the current minimum distance is greater than the distance to the rectangle, to the sibling. And that means there is a good chance, actually, that there's a point that are closer to the query point than the current minimum point. So we decide to go to the next bucket, which is this one, the sibling bucket, and then do the search again in the next bucket, which is over here. And then as a result of that, let's say, after visiting, all points over here, let's say we found a point that is actually closer than the current minimal point, the current closest neighbor. And using that, we're going to update the closest neighbor. And that's our new D mean, right? So that's our new D min. And what we do is then, okay, we just completed the search, over this bucket and this bucket. And effectively, that's all about this node over here, P9 node. So we completed the search for P9. Now, the sibling of P9 is this P6 node. Now, should we conduct a search on the P6 node? And the answer for that can be determined by comparing, so should we conduct a search on the P6 node? And that, question can be answered by comparing the minimum distance from the query to the current closest neighbor and the distance from the query to, the decision boundary, which is the P7 line over here. And the distance from query to P7 is greater than the current D mean, which means there's no chance that, any point in this bucket over here may fall into this circle. Okay. And what that means is there's no chance that a point in this bucket may have a smaller distance to the query point than the current closest neighbor, right? So then what that means is we can skip this entire P6 node because it's not worth it. Now that means we have just completed the search over the P7 node, and the neighbor to the P7 node is this sibling over here, P2 node. And again, the decision boundary for that is this line over here, and the query point is further away from this L1 line compared to the distance from query to the current closest neighbor. And therefore, again, the same logic, there's no chance that a point in this bucket on the left-hand side may actually fall into this small circle over here. So without really having to search through this buckets over here, you can just skip the entire thing. And with that, instead of visiting all the nodes and all the sections and do the search, we can limit our range of search into these two buckets. So effectively, we actually searched for these two buckets, nothing else. So that's basically the logic, in terms of why we don't go to the other buckets again. And obviously, by comparing just the siblings are obviously the ones that are closest to the current bucket. So instead of visiting all the buckets and do the exhaustive search, in this way we can make the algorithm more efficient. So hope that answers the question. If you have any follow-up question, please feel free to just drop it in the chat pod. In the meantime, so regarding the dimensionality, so back to my question again, the question was, is KD tree suitable for big data? And to answer that question, you need to consider 3 V's of big data. One is volume, the other is velocity, and then the last one was variety, right? So those are 3 V's that we learned from the first class. Now, I think 2 lectures ago, we have evaluated the KNN algorithm, right, in terms of volume, velocity, and variety. And then the conclusion there was, well, different people had different conclusions, but many of the people agree that the KNN algorithms are not so suitable for big data because in case of large volume, we see this problem. In case of high velocity, we see that problem, and so on and so forth. Now, we're going to do the similar analysis on the KD tree algorithm, okay? And we're going to try to see if KD tree algorithm is actually suitable for big data in the context of volume, velocity, and variety. So since we have actually a bit of time today, instead of me talking all the time, what about I put you guys into the breakout rooms? I'm not going to give you too much of time though, because we have some other materials that we have to cover today. But I'm going to, put you guys into the breakout rooms and maybe give about 5 minutes. And, why don't you take a time to, briefly discuss, what's going to happen when the volume is large, or when the velocity is large, and when the variety is large to the KD tree algorithm. Okay, so I'm gonna break you out into 3 to 4 people in a room. All right. So anybody had any interesting thoughts or idea that they want to share? You can feel free to drop that into the chat box. No one? Oh, nice. Yes. One of the comments that I'm seeing here is that what happens if we have 3, 4, 5 dimension, or even more, right? That's actually a question relevant to the variety of the data. So, I mean, I might be oversimplifying, but in terms of volume, we have large N, right? And then in terms of variety, we have large D. So just now we talked about a two-dimensional example, but what happens if we have a larger D, maybe 3-dimension, 4-dimension, 5-dimension, or even more? What's going to happen? Does anyone think that KD3 is going to be still robust when the D is large? The answer first, yes, that's true. The reason is, well, let's think about this. For a one-dimensional space, which is essentially a line, to split this into sections using binary trees, we just need the one partition line, and that partition line is going to partition the space into 2 sections. In case you have 2D, then you need 2 partition lines because you have 2-dimensional space, and then using the 2 partition lines, one time horizontally, one time vertically, you end up partitioning the space into 4 sections. So that's the amount of partitions that you create by kind of circulating around the different coordinates. So when you have only one dimension, which means you have only x-axis, and to circulate around all the dimension, which is in this case just 1, right? We end up having 2 partitions. When you have x and y coordinates, then you got to partition the space into x-axis and then partition the space in the y-axis. And as a result of that one round of partitioning, you end up having 4 sections. Now, in case of 3D, you're going to need 3 partitions, one time along x-axis, and then along y-axis, and then along z-axis. And as a result of that, how many partitions do we have? We have total 8, right? So you can kind of find a trend. In fact, the amount of partition that we end up creating by looping around all the coordinates is 2 to D. Okay, this is the amount of partition that we're end up creating. In case of D equals to 1, 2 to the D is is just 2. And then in case of 2-dimension, we have 4. In case of 3-dimension, we have 8. In case of 4-dimension, we have 16. In case of 5-dimension, we have 32, and then 64, and then 128, and it increases literally exponentially, right? And what that means is you end up splitting the space into so many partitions. And if you have so many partitions, then you may end up partitioning the space in a not so effective way. You may end up having a partition that has only 1 or 2 point, or if not empty at all. Whereas at the same time, you may have still a partition that still needs to be further divided. You see what I mean? So in terms of the effectiveness of partitioning, as we increase the dimensionality, it becomes much less effective. And if you also think about the search process, the fact that you will need to partition the space 3 times in order to go around one cycle of XYZ in case of 3D, then that's actually more tree nodes compared to the 2-dimensional case. Now 3D is kind of okay, but let's say your D is 100, which is quite common in many machine learning problems, right? You can see a lot of machine learning problems where you have a feature vector that is 100-dimensional. And in that case, we have to search along the partition of 2 to the 100. And not only that, there's a lot of comparison that we need to conduct in order to do the search. So this is actually one of the important aspects of KD-tree. KD-tree is not good at all for high dimension. So AKA, if you have a large variety of data, then KD-tree is not really good. Okay, so that's the first thing that you really have to keep in mind. Okay, the first rule: if you have a large variety, KD tree is not the option. What about volume? Can KD tree handle a large volume? Okay, so I'm seeing in the chat somebody says, with volume, it might become easier to search, but difficult to grow. Yes, actually, that sentence in the chat kind of captures two aspects, right? Well, that's at least how I interpret volume and velocity. So both of them are concerned with, parameter n, the number of, data samples. When you have initially a large volume, then that's great. Okay, given that d is small. Okay, assuming that d is small, when you have large volume, no problem. You just do the, you just construct a KD tree and then make it more effective. Sorry, predefine the structure of that d-dimensional space. And then when a new data comes, you can simplify the search and limit the scope of search into a subsection of the data space, as opposed to searching over the entire space. So when you have a large volume, given that d is small, then KD tree is an option to go. And that's in fact what we just learned, right? So that's kind of a trivial question. In case of a large velocity, though, this is really case by case. Okay, large velocity means you have constructed a data like this, and as the time goes, you get to see lots of new observation, lots of new data coming into your database, and you get to have lots of new points added to the tree. So how do you handle that situation? And that's actually a good question that I wanted everyone to think about. So when a new point comes in, similar to what we did with the query, basically you need to just search down the, by crawling down the KD tree. So again, let's say this red dot over here is a new data sample that's added to the database. Then in real time, what you're going to do is to basically compare that red dot with the P5 node, which is this line over here. And the red dot is on the right-hand side. So we're going to go to the P7 node. And then P7 node, we have the red dot above the P7 line. So we're going to go up to this node over here, right? And then we're going to compare that with the P9. And then we know that it's on the right-hand side. So the new point belongs to this bucket over here. So what you need to do when you observe a new data is to register this point to this bucket. So the new point now becomes a member of this bucket. Again, when you see a new point, over here, you add that to the other bucket, and whenever you see a new point, you basically need to do the tree search and then see which bucket that the new point belongs to, and then basically just register that new point as a member of the existing bucket. Now, is it gonna work all the time? Well, it depends. Okay, there are situations where the data is not so much balanced, in a sense that instead of having a uniformly distributed data samples coming in across the entire data space, you may end up having new data coming in to mostly a few buckets, and then the other buckets are a little unbalanced. So you see a lot of new data points coming into a particular bucket or two, and then the rest is kind of all over the places. Then if that situation happens, the effectiveness of KD tree search is going to be very low. It's going to become gradually low, because once we start to see a lot of buckets, a lot of members in a bucket, then a time to search across the bucket is going to be really challenging, right? And because of that, we're going to end up spending a lot of time searching through this bucket. And therefore, we're going to start losing the practical advantage of using KD tree. So that's one thing to think about. Another thing to think about is, how large are you going to allow the new data points, the buckets grow? So depending on the implementation, when the data set has a large velocity, usually what people do is to set the limit. Because otherwise, if you just keep accepting new data points, it's going to explode soon, right? If you have a high velocity. So you need to somehow maintain the level of maintain the volume of the database. So in that sense, you need to make another decision. Okay, initially you have the buckets defined by these points. Now you may end up having the buckets that are getting closer to the limits, And then, if that happens, then you may, have to kick out some of the members from the bucket. So basically, you need to remove some of the members from the bucket, maybe based on the age, right, of that data sample. So the oldest data samples are going to, go away, and then, that will be replaced by new data samples and things like that. So again, when that kind of situation happens, you need to be careful, and you need to have some guarantee that the new data will come in a sort of an equal rate across different buckets. Otherwise, you may end up having a bucket that is filled with a bunch of new points, whereas you may also have a bucket at the same time that is filled with a bunch of old data points. And in that case, your KD tree structure is not going to be able to cope with, the concept drift, which is the, which is the drift of the current data distribution over time. So in case of streaming data, the concept drift is really an important problem that you have to tackle with. Maybe, 5 years ago, the customers in your restaurant was primarily, I don't know, certain, demographical population, but for whatever reason, your customer base has totally changed to, to a different demographics. And, the reason why you're doing big data analytics is because you want to serve your customers better way based on their, characteristics and their, I don't know, their lifestyle and things like that. So that's basically why you're using, data analytics softwares. And, if you cannot cope with that, concept drift effectively, then, you're not going to be able to predict their behavior, predict their, preferences, very well. And, having a KD tree that has, buckets that are, not so balanced across, in terms of the ages of the data points, then you're going to end up having that kind of, problems related to concept drift. So in case of velocity, it's really case by case. Again, the underlying assumption is you have a small d. If you have large d, no matter what, then you're not going to use KD tree. Okay, but when you have small d but have a high velocity, then you have to make a decision. Do I really expect to have the new streaming to follow the similar distribution to the current data distribution? If there's some guarantee of that, then yes, KD tree still could be a good option. If there's no guarantee for that, though, then KD tree is probably not the one that you're looking for. Okay. So that was kind of a brief, discussion about KD tree in the context of big data. Okay. If you have any question, again, please feel free to drop that into the chat window. I'm gonna just move on to the next slide. So here. Now, there are a couple other ways to fight against the curse of dimensionality other than the ones that I just mentioned. And one of the important things, I mean, there are many, but one of the things that I really want to emphasize in today's class is approximation. And this is particularly important message to, I don't know, engineers like myself, because we have this tendency of trying to be precise on everything. And that sometimes can be really problematic, especially in practical, problems. In math courses, in many other technical courses, we learn to be precise and train to be precise in doing things. But in some situations, you need to kind of lead with approximations, and that's especially true when you have a large amount of data. When you have large amount of data, then you probably don't want to be too pedantic and spend too much of time making sure that the nearest neighbor is indeed the nearest neighbor. Okay, I mean, what's wrong with having a second nearest neighbor as opposed to the nearest neighbor, or even third nearest neighbor? Assuming that we have large amount of data, then first nearest neighbor, second nearest neighbor, I mean, they're going to be still in the periphery of the given query point. And is it going to make a huge difference? Like, finding the rigorous nearest neighbor versus finding a sloppy nearest neighbor, meaning, second or third or fifth nearest neighbor. When you have millions of points, okay, is it going to really make a difference? When you have only 100 points, then yes, that might make some difference, right? The closest neighbor versus the third nearest neighbor. I mean, there's going to be a difference if you have only 100 data samples. But let's say you have millions of data samples. Does it really make any difference? And my argument here is not really, okay? And that's the spirit here, okay? So the reason why I'm arguing like that is because, first of all, the distance functions are not perfect. Remember the first lecture about the distance and similarity? When we introduced the notion of distance functions, we talked about two different things. One is the mathematical requirement of, as distance functions. So there are 4 requirements, right? Like including triangle inequality, the symmetry condition, and things like that. So those are the technical requirements to be a distance function. But in the meantime, we also talk about the requirement that the distance functions must be resemblant of the human notion of similarity in the context of that data problem, right? So you have, for example, images of a bunch of faces, okay? And you want to train a machine learning algorithm or whatever that recognizes different faces and classify, I don't know, their names or their gender or whatever. So that let's assume that kind of application. Now, the distance function between the faces must be defined in a way that indeed the notion of distance defined by that mathematical function resembles the ability for people to distinguish different faces. So, AKA, if 2 faces are difficult to distinguish for actual people, so like, identical twins, for example, then the distance values created by the distance function must be close to 0. Whereas, you have you have 2 individuals that are totally, different in their appearance, then the distance function must resemble that, difference somehow. Now, that was kind of the requirement for distance function. Now, I ask you, can you actually define a perfect mathematical function that can distinguish different human faces? I mean, is the human notion of similarity even quantifiable? Can we quantify how much different their appearances are using some numerical values? I don't think so, right? I mean, that's something that depends on a lot of different people. For example, in my case, I'm terrible at recognizing faces. So, for people I met on the road, and I seldom remember their, faces very clearly. And I have this dependency across different, ethnicity. So like, I grew up in South Korea, and I have observed a lot of data samples on South Korean population. But when it comes to like Europeans, Americans, I haven't seen them a lot as much as, what I've seen, Korean population. And therefore, my classifier, my notion of similarity, the distance function that I have in my brain works differently, right? Across different, different people, different races of, different people. And what I'm trying to say here is that the distance function are incomplete. They're not as accurate as you would think. Now, under this fact, is it really meaningful to try to find the nearest neighbor as opposed to just an approximate nearest neighbor, right? That's obviously something to think about. And yeah, so because of that reason, the argument here is, well, let's just move on. I mean, why do we even bother to find the nearest neighbor? Can we just, find something that is close enough to the query point and then just return the result, as rapidly as we can, right? And that's basically the idea of an algorithm called an approximate nearest neighbor, or ANN. That's not artificial neural network, by the way. And what you need to focus over here is this term 1 plus E. Okay, so E is kind of a range of tolerance. Okay, so let's say Z is an object, okay, that is closest to the query point Q in the current stage of computation. Okay, so at some stage of KD tree search, let's say Z was the closest neighbor. Now, what you're going to do is to make sure that Z is smaller than any other point in the data set X. But here, I'm adding this approximation parameter. I'm adding this tolerance. So instead of saying that, all points, okay, so when you compare the distance from Q to Z and the distance from Q to X, instead of ensuring that all points X have greater distance than the point Z, we're going to give some tolerance over here. So for some positive number E, if we say, if we multiply, let's say 1.2, then even if Z is the rigorous, even if Z is not the rigorous nearest neighbor, if you multiply 1.2 to the other points, then you have some, like approximately 20% of the, distance tolerance in terms of accepting Z as the closest neighbor. So what I mean by that is this is what's happening in the action. So here's the same example. Our concern was that, okay, P9, as a result of crawling down to this, bottom edge node of the tree, P9 turned out to be the closest neighbor. Now, our concern previously in the rigorous algorithm, our concern was that, well, the radius of the circle defined by P9 centered at the query point touches actually the sibling, which means that there is a chance that, even closer point than the current closest neighbor may exist in the sibling bucket. So what we did was to actually visit the sibling and then made sure that what we have is indeed the closest neighbor. And if not, we updated the closest neighbor with the actual neighbor that's found in the sibling bucket. That's what we've done in the previous case. Now let's introduce that tolerance factor, 1 plus E. What that means is the radius of the circle reduces down by the factor of 1 over 1 plus E. So again, for some positive E over here, the radius is going to shrink to a smaller radius. And if that shrunken circle does not touch the sibling bucket, then instead of bothering to visit the sibling bucket and do the additional search, we're going to just move ahead. Okay? We admit that there is a chance, of course, there is a chance that there is a, the real closest neighbor that we might be missing, but we're going to move on for the sake of time, right? Let's not be pedantic and let's just move on. Let's just move on with an approximate neighbor. And that's basically the idea of accelerating the search, okay, from this original KD tree implementation. So E is the accuracy factor or the tolerance factor. If you set E equals to 0, then obviously what you're going to do is to, hey, I want the precise, rigorous nearest neighbor. But if you set E to be something bigger than 0, then you're kind of giving a little bit of tolerance. Okay. So that's kind of, one of the ideas of that's the underlying, motivation behind the approximate nearest neighbors. Okay. So again, when you have like 100 samples, 200 samples, it doesn't really matter. But when you have millions of samples, then there's, in terms of depth, you're going to have a limitation in terms of, how detailed you can be. And approximate nearest neighbors are usually, working very, well, as opposed, compared to the rigorous nearest neighbors. And in fact, probabilistically speaking, the cases like this particular query is very few, especially when you have a large data set. Probabilistically speaking, approximate nearest neighbors, quite a good fraction of the time, they indeed return the rigorous nearest neighbors, okay, not the approximate ones. And probabilistically, there are, only very small cases where the actual nearest neighbor exists in a, in between this small circle and the large circle. Okay, so, it sounds like we're, compromising a lot, but in fact, we're not giving up too much of accuracy. So that's kind of a spirit of, nearest neighbor search in the context of large data set. Okay, and in fact, the next class, well, actually 2 lectures from now, we're actually going to talk about what is called the Nystrom approximation. Nystrom approximation is a way to approximate the distance. Same logic, instead of being pedantic, because the distance functions are incomplete and they're not perfect representation of the notion of similarity. So why bother to be precise and be pedantic? Let's just move on, right, with a quick search. So that's kind of, the main takeaway message from the lectures that I'm, delivering here regarding the distance and similarity. I hope that message is clear to you guys. Okay. So we kind of discussed this, in the previous slide. So I'm going to just skip ahead. It's about the, when D is really large. So we already talked about it. Now, here's another algorithm called locally-sensitive hashing. Okay. To give you the conclusion first, LSH is effective for the cases where KD trees cannot handle very well. AKA, when you have a large dimension D, then LSH can be considered as an alternative to KD trees. Okay. So I mentioned that KD trees are okay with small d, and even if you have large velocity, large volume, KD trees should be able to handle them fairly well. But when d goes up, then there's no choice for you with KD tree. So for that particular scenario, LSH is something that you may want to consider using. Now, considering that this class has a good mixture of computer science students and students from different major, I think many of you may not know the notion of hashing. So for those people, I'm going to give you this toy example. Let's consider a data space that is defined by a number of the word amazing mentioned, and then the number of word terrible mentioned. And let's assume that we're talking about a Netflix movie review data set. So what you're going to do is each data point represent a movie review. And what we're going to do is simply count how many times people mention the word amazing in that review, and then how many times they mention the word terrible in their review. And then we're going to use them as a feature vector describing the review in a, of course, very rudimentary fashion. Okay. Now, in this space, now assume that there's a mathematical function defined as fx, which is basically, number of amazing minus 1.5 times the terrible. And using that, what we're going to do is to classify the movie reviews into two buckets. Okay. So for example, X1 has 0 and 4. So 0 number of words amazing is mentioned in this first review. And but this reviewer mentioned terrible 4 times in the review, so the movie must be really horrible, right? So in this case, the function value fx1 is evaluated as 0 minus 1.5 times 4, which is what? -6, right? So then the function value of x1 is -6. If you consider the next point over here, we have 2 times amazing minus 1.5 times 2 times terrible. So again, it's still a negative number, right? So this is -1, and that's fx of 2. So we can, do this kind of computation for all the data points, and then as a result of that, we're going to have a number that is associated with each of the movie review. It's going to be either negative or positive. And in case you have, based on that, what we're going to learn is that, with respect to this line over here, anything below this is going to be positive, right? The sign of the function f is going to be positive, and then the sign of function f on the upper half of the space is going to be negative. And in that way, using that, mathematical function f, we can construct a table that says data point x1 has a negative sign, data point x2 also has a negative sign, data point x3 has a positive sign, and so on and so forth. And in case when the data point has a positive sign, then we're going to give them an index of 1, and then when the sign is negative, we're going to give them an index of 0. Okay? And if you write this table with respect to the 0 and 1 labels as, columns, then you can, you can list the data points that falls under the category of the negative sign and the points that falls under the category of positive sign, right? And using that, you can actually develop a structure within this data space. So it's kind of similar to KD tree. In case of KD tree, we basically have selected a median point along the horizontal axis, and then we partition the data into two buckets. What we're doing here is, instead of those perpendicular lines, we're just drawing an arbitrary line defined by this linear function f, and then we're partitioning the space into two with respect to that function f. Okay, so that's what's happening over here. And at the end of the day, we created two buckets, okay, in this toy example. Now, using this bucket, which we call hash table, what we're going to do is, okay, for a given query point, let's say there's a new movie review came in, and then it contained the word amazing 3 times, and then the word terrible only 1 time. And if you compute this this formula over here, 3 minus 1.5 is positive 1.5. So the classification of this query point is going to be a positive sign. The positive sign corresponds to the bin index of 1. And what that means is you don't actually need to find the nearest neighbor from the other bucket. You can just simply ignore this, but rather focus on your similarity search within this bucket. Does that make sense? So it's basically the same idea as KD tree, right? Instead of visiting the entire space, instead of traversing the entire set of data, you're gonna, somehow divide the, space into, different buckets. And then whenever there's a new point coming in, we're first of all going to find which bucket the query point belongs to. And then based on that, we're gonna find the nearest neighbor only within that bucket, okay, where the query point belongs to. Okay. Of course, we have the same issue. For example, let's say the query point is this green point over here. And based on the hash function f, the query falls into this bucket, the upper half. And from there, if you find the nearest neighbor, this is going to be the nearest neighbor. Whereas there is indeed a point on the next bin, next bucket, where it is actually closer to the query point. So that's the exact nearest neighbor, which is the same problem as the KD tree, right? In case of KD tree, we had the same issue. So again, in case of LSH, you can use that safety factor, 1 plus E thing, multiplied to the inequality that we saw in the previous slide, right? And then maybe kind of give a little bit of tolerance in terms of how exact you want to be. But in the meantime, you also want to find a way to actually deal with this kind of cases. Okay, so those are the things that we need to discuss in terms of how to define LSH algorithm. Now, another thing is, look at this function f. I mean, where did this function came from? Like amazing minus 1.5 times terrible. Like, how did I determine the numbers? Right? And the numbers actually define the slope of the line. Slope and the y-intercept of the line is going to be determined by the parameters that we're putting here. And in order to split the data samples into buckets, and we want the buckets to have approximately the same size across the buckets, so that in terms of search speed, we have a good balance over different buckets. And in order to satisfy the condition, how do I, what should I do to come up with those coefficient of the linear function, right? Is there a way to determine the good number for those, coefficients of the linear equation over here, right? So those are the 2 major topics that we're going to discuss in the next class, which is going to be on Thursday. And then on Thursday, we're going to kind of wrap up this lecture about the distance and similarity and the search algorithm. And then we're going to move on to this topic called the Nystrom approximation, which provides you a method to approximate distances. Remember, when we first introduced the distance and similarity problem, we classified them into 2 categories. One is the nearest neighbor search problem, and then the other was all pair similarity problem. So far, we've been talking about the nearest neighbor search problem, and we never really talked about the all pair similarity search problem. So the Nystrom approximation is going to be, an effective method for the second case. What we've talked about so far is mostly for the first case of the problem. So that's kind of the plan for the next. So thank you guys very much, and I'll see you on Thursday.